Welcome to the webinar about measuring methods, scope, and applications of thermal conductivity and thermal diffusivity of thin films. In this context, the instruments Thin Film Laser Flash Analyzer and Thin Film Analyzer are introduced and shortly described. Linseis Thermal Analysis manufactures instruments for thermal analysis and determination of thermophysical properties. The family-owned company was founded in Selb, in Germany, in 1957 by Dr. Maximilian Linseis, who is shown on the left picture. Today, the company is led by the second generation, Klaus Linseis, shown on the right, and also the third generation has become an established force in the company. Starting with the development and production of dilatometer and DSCs for the characterization of ceramics and porcelain, for which the region of northeastern Bavaria was famous for, Linseis emerged as one of the most innovative and leading companies in the field of thermal analysis and measurement of thermophysical properties. Next to its headquarters in Selb, Germany, Linseis has owned subsidiaries in New Jersey, USA, as well as Shanghai and Beijing in China. Furthermore, Linseis has representatives and customers in more than 70 countries worldwide. Linseis Thermal Analysis manufactures instruments for thermal analysis of materials and the determination of the thermophysical properties. The product range includes a complete lineup of analyzers, such as differential scanning calometers, thermal balances, simultaneous thermal analyzers, which is a combination of the DSC and thermal balance, dilatometers, thermomechanical analyzers, instruments for the measurement of thermal conductivity and thermal diffusivity, and instruments for the characterization of thermoelectrical materials, and last but not least, instruments for the investigation of the physical properties of nanometer thin layers. For a more detailed research, the thermal analyzers can be coupled to gas analyzers such as mass and infrared spectrometers. Linseis, as an innovative and solution-driven company, also has strong capabilities to realize modifications on a standard portfolio or even build unique tailor-made instruments. Before we come to the actual webinar, I would like to introduce myself briefly. My name is Erika Hahn and I studied physics at the University in Erlangen. At Linseis, I am responsible for the thermal transport measurements in the application laboratory. And here comes the outline for today. We will start with a brief introduction into the field of thermal conductivity and thin films. After that, we go further to the application fields where the knowledge of the thermophysical properties is important. Under point 4, we will show you why the classic metrology, like a laser flash, is no more applicable to thin films, and why it is required to develop and introduce more dedicated measurement techniques. With the next two topics, we will show you our two platforms, TFLFA, which stands for Thin Film Laser Flash, and TFA, which stands for Thin Film Analyzer, more in detail. The presentation will be closed with a short summary and point you to some interesting publications. In addition, please do not hesitate to contact us whenever you have questions or would like to discuss applications. Before we have a look at the commonly used measurement techniques and instruments, the next two slides will give a very brief introduction in the theory of heat transport. Fundamentally, there are three ways of heat transport: radiation, convection, and conduction. Our products mainly focus on how much or how fast heat can be transported within a material, and thus we focus on the thermal conductivity. And the total thermal conductivity of a material consists of a phononic and an electronic contribution, where the phonon part are mainly waves of lattice vibrations and the electronic part are free-moving charge carriers which transport heat. If we now classify different types of materials with this knowledge, we know that the heat transport in highly conductive materials, like metals, is dominated by the charge carriers. Thus, the thermal conductivity of these materials can also be calculated by using the Wiedemann-Franz law. For that, the electrical conductivity needs to be measured. This can be an advantage, as electrical transport measurements often are easier to carry out than thermal transport measurements. Nevertheless, in semimetals, semiconductors, and isolators, the phonon contribution is not negligible and can even be dominating, and thus also approximations get more complex or are not possible anymore. Another important point for the introduction is that a distinction must be done between thermal conductivity and thermal diffusivity. Both properties get mixed up very often when it comes to measurement techniques. The big difference is that thermal diffusivity gives the speed of a temperature spread within a material, so how fast a material can conduct heat, whereas the thermal conductivity gives the amount of heat which a material can transport. This difference can also be obtained if we have a look at the SI units, where thermal diffusivity is given in meters squared per second, whereas the thermal conductivity is given in watt per meter Kelvin. Most of the time, there is more interest in the thermal conductivity rather than the thermal diffusivity. But some techniques, like the often used flash techniques, measure the thermal diffusivity. And for that reason, it is important to know that the thermal diffusivity and thermal conductivity are linked with each other by the density in a specific heat, which makes it rather easy to convert both properties. Nevertheless, these properties are also temperature dependent, which makes a temperature dependent characterization of all involved parameters necessary. Of course, people measure the thermophysical properties for several reasons, but the next slide should give an idea why there is interest in the investigation of the thermal conductivity and where typical application fields of our instruments are. One big application field is research, so that the fundamental transport mechanism can be understood. Apart from that, the knowledge of the thermal conductivity can be very helpful, especially in the area of nanoengineering, size effects, and surface effects, like they are described by Meyer-das-Schatzkes or Fuchs-Sondheimer, play a big role and are still in the focus of research. But also apart from that fundamental research, the knowledge of the thermal conductivity can be very helpful in industrial applications. For example, it is a crucial parameter for the design of devices. For example, the design and heat management of devices like CPUs or most modern 5G telecommunication chips, which have very high power densities, the waste heat treatment is a big issue. If the temperatures and especially gradients are getting too large and an efficient removal of the waste heat is not possible anymore, parts can be damaged or may fail in consequence of thermal stress. Another example is that the thermal conductivity can be used for quality control. The thermal conductivity can be an indicator for the material composition or defect structures. For example, the result of surface ion implantation on a wafer can be monitored by using a TF-LFA, by mapping the thermal diffusivity of the surface area of the wafer. And another application is the simulation of heat transfer. For an accurate simulation using finite element analysis software, accurate input parameters are required. And this is the point where metrology is required, as thin films very often behave completely different compared to bulk material. But why do thin films behave different? The physical properties of thin films are different from bulk material because the parasitic surface effects are much stronger due to the smaller dimensions and high aspect ratios. That means that the surface parts play a much bigger role than in bulk material. And the weight of this influence depends on the volume to surface ratio and is thus thickness dependent. If we have a look at a simplified model, we see that charge carriers or phonons can move in any directions in a 3D body. whereas they have restrictions in movement when we come to a quasi-2D body like a thin film. In addition, thin films are very often polycrystalline, which means the grain size distribution, which also depends on things like deposition technique, thermohistory or thickness, also influences the transport properties. We can see how big this influence of nanostructuring on the transport properties is when we have a look at the diagram on the right side. It shows the thermal conductivity of silicon nanowires independent of the diameter. We can see a clear reduction of the thermal conductivity with reduced diameter. Another important point about thin films to mention is that they show anisotropic behavior in most cases, what makes a direction distinction in plane or cross-plane very important. We will prove these assumptions later with actual measurements. Before we come to the characterization techniques, it needs to be defined what we understand by a thin film and where the differences are. Fundamentally, a thin film is a layer with a thickness somewhere between a few nanometers to a few tenths of micrometers. These thin films get deposited on a substrate, which can be a silicon wafer or some kind of insulator, like silicon nitride or quartz glass, but can also be a microchip, like our integrated TFA chip. Now the thin film needs to be prepared, they need to be deposited. And for this, a large amount of possible techniques exist, like physical vapor deposition techniques, shortly PVD or CVD techniques, like plasma-enhanced chemical vapor deposition, PECDV, low-pressure CVD, or atomic layer deposition, shortly ALD. But there are also rather easy and fast applicable deposition techniques, especially from the liquid phase, like spin coating, printing, or drop casting. After the preparation, thin films are used in many different application areas, from semiconducting thin films, for example for sensors, transistor, or thermoelectric applications, or metallic films for interconnections to thermal barrier coatings and optical coatings. If the films are thicker than a few tenths of microns, or should be freestanding like a foil, we don't call this a thin film anymore, but maybe freestanding film or coating. For this, we use another kind of measurement equipment like our standard laser flash analyzer or TIM tester. You can find matching webinars for these machines on our website as well. But now let's come back to the thin film characterization devices. For this application, Linseis developed two powerful platforms. The first one is an optical characterization technique, a derivative from the standard laser flash technique. And the second one is a unique chip-based platform using a hot wire technique in combination with the 3-omega method. Both systems can characterize thin films from the nanometer to the micrometer range and can operate from sub-ambient to elevated temperatures. One important thing to mention is that the TF-LFA measures the thermal transport properties in the cross-plane direction, whereas the TFA measures it in the in-plane direction. The first device to have a closer look at is the TF-LFA, the thin film laser flash. In the figure, the basic setup, which is built up on an optical bench, can be seen. In order to explain the extensions of the TF-LFA setup compared to a standard LFA machine, the principle of a laser flash measurement according to the ASTM E1461 norm will be described shortly. The norm describes the experimental setup in detail, which is schematically shown on this slide. It consists of a neodyne YAG laser, which is used to heat up the backside of a sample using a very short heating pulse, and an infrared detector with a high-speed data translation card in order to detect the temperature rise on the front side of the sample and measure the time it takes for the thermal wave to conduct through the sample. In the last step, the signal from the detector will be post-processed and recorded by the integrated electronics and software. So, after the measurement, one obtains a graph which shows the normalized temperature rise on the surface over time. For the calculation of the thermal diffusivity, one needs to determine the baseline and the maximum temperature rise, determine the half-time required from the initiation of the heating pulse to reach the half of the maximum temperature rise. This time is called T1 half or half-time rise. With this knowledge, we can calculate the thermal diffusivity according to this very simple formula, where alpha is the thermal diffusivity, L is the thickness of the sample, and the half-time rise, T1 half. This experimental setup works good as long as the timescale for the measurement is not too short. But the higher the thermal diffusivity of the sample is and the thinner the samples get, the bigger the measurement error gets. You can see an illustration of this correlation in the graph on the right side, published by Seebeck. It is also rather easy to imagine that a thermal wave, which is conducted through a 3 mm thick polymer sample, takes much longer to reach the front surface than the thermal wave through a 100 nanometer thin gold layer. This is illustrated in a table which lists the thermal diffusivity and minimal height of different materials for the LFA measurement. The timescale changes from the millisecond region to the nanosecond timescale. And because of this, the classical laser flash technique runs into two main limitations. The first one is the problem to acquire enough data points within the short time period of the experiment. And the second one is the overlapping of the heating pulse on the backside with the temperature rise on the front side. Both effects lead to a measurement error depending on the sample thickness and thermal transport properties. Even most modern 2 MHz data acquisition and most powerful laser sources with short pulse duration are not powerful enough to measure thin films using this technique. And this is where a new experimental setup and an advanced approach is required. For our TF-LFA setup, we use a nanosecond laser with a pulse length down to 1 nanosecond, compared to a neodymium pulse laser, which has a pulse length in the millisecond region for the standard LFA. And in order to acquire enough data points for the detection of the temperature rise on the front side, we use a faster and more suitable detection method, which is called thermoreflectance. We use the fact that the reflectivity of a material is temperature dependent for the measurement of the local temperature rise. For this, a secondary detection laser continuously measures the reflectivity of the heated spot in order to record its normalized temperature. This is used for the determination of the thermal diffusivity. To be able to perform the measurements with this method, a reflective layer with a known reflectivity behavior independence on the temperature is needed. So when we now use the classical laser flash setup and simply change the limiting components, we come to a configuration like this, which is called RF configuration. This is derived from rare heating and front detection. With a nanosecond pulse laser and a continuous wave detection laser in combination with a high-speed silicon photoreceiver. In order to detect the local change in temperature, we need a transducing layer, which needs to match with the wavelength of the detection layer. In our case, we either use a 473 nanometer in combination with gold or 785 nanometer in combination with aluminium or platinum. These are the two most commonly used wavelengths. In the end, the experimental data looks very similar to the standard laser flash, with an increasing edge, which we use for the evaluation of the thermal diffusivity of the sample. Only the time scale is different. Nevertheless, there are two main disadvantages of this configuration for the measurement of thin films. The first one is that we need a translucent substrate, which allows the laser beam of the heating laser to pass through and only absorb at the back side of the sample. And the second one is that even with a nanosecond pulse laser and high-speed data acquisition, thin films must be in the range of hundreds of nanometer to micrometer for a measurement. And because of this, the TF-LFA can also be used in a second configuration, which is the real standard configuration. In this case, the heating and detection takes place on the sample side, the front side. This configuration is called FF, front heating, front detection. What happens is that we locally heat a small spot on the front side of the sample with a short heating pulse and have a look at a subsequent temperature decrease of the spot. Here again, the signal is evaluated in a time domain, which, by the way, is the reason that this technique is called time domain thermoreflectance. Depending on the underlying materials, the cooling curve will be influenced. For example, if there is a high conductive layer below, the cooling will be much faster than when there is a low conductive layer below. In order to calculate the exact thermoconductivity of the sample layer, we need to use a multi-layer heat flux model, which accounts at least for the transducing layer, the sample layer, and the sample. This is also the case for the RF configuration. For the most accurate evaluation, we work together and have a cooperation with Professor Dr. David Cahill, who is a world-leading expert in the field of nanoscale thermal transport. And this is what the TD-TR measurement looks like for two molybdenum thin film layers on the same substrate, but with different thicknesses. What we see here is the heating pulse at time 0, showing the normalized temperature peak and the ongoing temperature decrease of the heated spot over time. It can be clearly seen that the thickness of the molybdenum layer has a big influence on the cooling curve, showing that the thicker layer, the faster the spot cools down. And this is because of the fact that the thermoconductivity of the layer decreases with the thickness. This is a typical behavior which can be obtained and can be explained with the previously introduced size effects. In order to make the data acquisition fast, easy, and reliable, we developed a user-friendly software environment. The environment consists of a measurement program in order to perform the experiment and an evaluation software which is used to evaluate the measured data, according to the multi-layer model developed in cooperation with Professor Cahill. On the one hand, the software environment is designed to make the handling as easy as possible, and on the other hand, the software and also the setup itself are designed to allow a maximum in flexibility. Another very important feature is our unique sensitivity tool, which allows to simulate a certain measurement before doing the measurement in real. This helps to learn if a measurement will be successful or what parameters you have to pay attention about. For example, optimizing the transducing layer in order to see what its optimum thickness is. So, to sum it up, with the TF-LFA, Linseis developed a powerful tool to characterize thin film samples from the nanometer to micrometer scale, regarding their out-of-plane thermal transport properties. It is a further development of the standard laser flash technique for the measurement of thermal diffusivity. For the determination of the thermal conductivity, the density and the specific heat capacity are needed. The used measurement method requires a transducing layer of approximately 100 nanometer, as well as very smooth surfaces for the measurement. The big advantage is that it is an optical measurement and thus can cover a broad temperature range and is nearly free in the choice of substrate. On the right side, a typical study for the thickness-dependent thermal conductivity of a silicon nitride layer is shown, where one can see that the thermal conductivity decreases with layer thickness. The next device we present you today is the TFA, the Thin Film Analyzer. The TFA is a chip-based platform where the chip is a disposable sensor to which the thin layer is directly applied. Furthermore, all sensors and contacts are integrated in the chip. The instrument is built up modular and can not only measure the thermal conductivity in specific heat, but also the electrical conductivity, the Seebeck coefficient, and the Hall constant of a thin film sample. The TFA was developed to raise complex thin film characterization procedures to a new level. Because of the integrated microchips, which can be produced on a large scale, the complex experimental setup as well as the measurement routine has been mostly standardized. This brings enormous advantages regarding sample preparation and data evaluation effort. Once the sample is properly deposited on the chips, the system can find the matching measurement parameters automatically, and the evaluation is a true on-button solution. Only the thickness of the film has to be inserted for the evaluation. As the research field for thin films is rather broad, the TFA has already been tested with a big amount of samples, produced by varying deposition techniques, from PVD to CVD to spin coating and inkjet printing. Next to the flexibility, another focus has been put on the consistency. As we can use the TFA as a platform, we can measure different parameters nearly simultaneously, and in the same direction, the in-plane direction. The TFA measures the thermal conductivity, not diffusivity, directly and can also be used to measure the specific heat capacity of thin films in a basic version. This version can be further upgraded for electrical conductivity and Hall constant measurements. From this, it is possible to get information about the charge carrier concentration and Hall mobility. And this allows to get a comprehensive picture of the material, and every event or trend can be seen on all parameters simultaneously. Because we need only one sample, many measurements errors like different sample composition, different sample thickness, different heat profiles, or environmental conditions can be omitted. This slide shows the unique measurement concept a bit more in detail. From the starting point of a sample material, which can be a solid target, like shown here, but which could also be a solution or a sample deposited from the gas phase. The sample gets deposited on the pre-structured measurement chip. There are two main structures on the chip, which is a hot wire setup in order to characterize the thermal transport properties, as well as a 4-point configuration, which allows to characterize the electrical parameters. The deposition routine depends on the conditions, of course, but is designed to be rather easy. We use kind of masks for protecting the connecting parts of the chips during the deposition. After the sample is deposited on the entire front side, we remove the mask and have the residual sample in the designated areas only. Once the sample is deposited on the chip, we can insert the chip to the measurement chamber and start the measurement. For the measurement, different configurations regarding the temperature profile, magnetic field, and atmosphere are possible. Setting up a measurement profile and the evaluation of the measurement can be done using the integrated Linseis software package. Here, the same software and database as with other Linseis instruments can be used. On this slide, you can see the central part of the system, or a patented microchip. The integrated microchip consists of several miniaturized experimental setups. For example, 2 suspended membranes, several on-chip heaters, electrodes, and a resistance thermometer. The membranes are mainly used for the thermal transport and Seebeck measurements, and the needle contacts for the Hall and resistivity measurements. The front side of the chip is mostly covered with an insulating layer. Thus, the sample is not forming a short circuit with the on-chip heaters. The empty chip can be seen on the left side and the covered chip, ready to measure, on the right side. Now, if we have a more detailed look into the thermal conductivity measurement, we can see the two membranes with different areas. If we cut through the chip and have a look from the side, we get the cross-sectional view, which can be seen on the right side. Each membrane has a hot wire aligned to the middle axis, which we use for heating, but also for temperature sensing. For the measurement, we apply a known heating power to the hot wire, which causes a temperature rise in the middle. The silicon rim acts as a heatsink, and because of the large aspect ratio between length and width, we get a nearly ideal 1D heat flux from the heater in the middle to the surrounding rim. As we know the geometry of the membrane, we can calculate the thermal conductance of the membrane, or membrane plus sample setup, by measuring the occurring temperature rise of the hot wire, independent of the applied heating power. For example, the higher the thermal conductivity of the sample, the smaller is the temperature rise of the hot wire and constant heating power. As we do not use constant current but alternating current to drive the heater, we can use the third harmonic of the voltage drop along the heater for the temperature measurement. That's why the measurement technique is called 3-omega measurement technique. The last point to mention on this slide is that we use a two-membrane setup, which allows us to account for the radiative heat loss. This is an important point, as the surface-to-volume ratio for thin films is large. For the evaluation of the thermal conductivity of the sample, we use a differential measurement of the coated and uncoated chip. Because of this, the thermal conductance of the empty chip is an important parameter for the sensitivity of the chip, as it defines the measurement range. If the influence of the sample layer on the thermal conductance is too small, the measurement accuracy will be bad. Nevertheless, as we use an only 100 nanometer thin silicon nitride membrane in combination with a powerful lock-in amplifier, this gives us a very broad measurement range, as can be seen in the table. With the next two slides, some remarkable measurements are presented which were done with this platform. The first one was a typical thermoelectric sample, bismuth antimony, where strong size effects were shown, which impact all transport properties, thermal and electrical. Both have been heavily affected. In addition, the impact of thermal annealing on the transport property was shown, as a thermal cycle was measured. If you are interested in more details, the study has been published in the Journal of Semiconductor Science and Technology, where a lot of further findings like thickness dependencies and the influence of annealing on the thermoelectric films are presented. The second measurement which is presented is a measurement of a 100 nanometer thin gold layer, as this impressively shows why thin film characterization is so important. Gold films are very often used in semiconducting industries as contact material or heat spreader. Our measurements again clearly show the influence of size effects on the properties. While bulk gold has a very high thermal conductivity of about 320 watt per meter Kelvin, the thin film has been measured with about half of this value. And also, the electrical conductivity is reduced compared to the literature for bulk material. The knowledge of this data is crucial for the design and simulation of future high-tech products like 5G telecommunication chips, in order to achieve a sufficient heat management and prevent them of failing. If you are interested in further details about the techniques and applications, I would like to suggest our website. There, several applications of groups around the world using our systems can be found. Or, if you are more interested in the experimental setup and how the system works in detail, I would like to suggest these two publications. The first one describes the chip and measurement routines in detail, and the second paper describes the limitation of the thermal conductivity measurement regarding minimum and maximum thickness of the samples. Last but not least, I would like to briefly advertise our other products for thin film measurements. As we have a very comprehensive product lineup, we can always offer the best matching solution for the measurement task. The thermal conductivity and thermal diffusivity of thin films can be obtained by using the in this presentation shown TFLFA and TFA. However, for some samples there is also the option to use a thin film adapter and use the standard laser flash analyzer LFA. The Seebeck coefficient and resistivity can be obtained by the TFA, the LSR using an adapter, or one can also use the Hall characterization system for determining the resistivity. The Hall coefficient can either be measured by the TFA or the just mentioned Hall characterization system. So much for thin film thermal transport characterization, which should give you a good overview of the Linseis product lineup for the characterization of thermal transport properties of solids, liquids, pastes, pads, greases, coatings, and many more. If you are interested in the characterization of bulk thermal conductivity, please have a look on the separate webinar Thermal Conductivity and Thermal Diffusivity Measuring Methods, Their Differences and Applications. Thank you very much for your attention.